Dear students, welcome to the fourth lecture on homology theory. So in the last lecture, I have computed the simplicial homology group of torus. So today I shall start with Rp2 and I shall compute the simplicial homology in a simpler way. So here is the problem. Find the homology groups for the topological space Rp2. Okay, so we have already seen the delta complex structure on Rp2, that is this one. So this, suppose this is my U, this is L, right? Say this is the edge A, then this will be A. If this is B, then this will be B, and this is C. Okay, and here I shall first write here, it is say V0, say this is the V1 and this is the vertex V2, and here it is V2, and I shall take the orientation V0, V1, V2. That's mean in this way. Okay, and here you can see that since we have to identify the antipodal points, so V0 will be same as V1. Okay, so shall I need to recall what is Rp2? Okay, I can recall that one. So Rp2 means it is D2, that is you have to take one disk with some identification where x identified with minus x whenever x belongs to the boundary of the D2. That's mean you have a disk, okay, and you have to identify this x with the antipodal minus x. So this identification only on the boundary circle. Okay, so this is my definition Rp2, and we have seen that this is a delta complex structure for Rp2. Okay, now here to compute the homology, we have to find first of all that delta n Rp2. Okay, so here we write first of all delta 0 Rp2 as span of the vertices V1, V2, and delta 1 Rp2 is span of, actually by the definition it is thus it is spanned by the maps, right? Maps from the one dimensional simplices to X, but here all the maps are uniquely determined by the ABC, right? So here I can write A, B, C. So you can think that ABC as a map, or you can think as an image of the simplices. Now delta 2 Rp2, that is spanned by U and L, right? And delta n Rp2, that is 0. So therefore we have map, we can write this for all n greater equal to 3, and we have that is delta 3 Rp2, which is actually 0, to delta 2 Rp2, delta 1 Rp2, delta 0 Rp2, and that is 0. So this is a del 0, and we know this is also a 0 map. This is my del 1, this is my del 2, and this is del 3. Since delta 3 is 0, so this is also 0. Okay, now what is my delta 2 U? So this is boundary of U. Now note that so to find the boundary we have to choose the orientation, right? In the last lecture I found it through the maps, right, that v0, v1, v2. You can apply this one as well here. So instead of taking the map, I shall write u restricted over that v1, v2, then minus u restricted over v0, v2, and then plus u restricted over v0, v1. Okay. Now what is my u restricted over v1, v2? So this is my v1, v2, right? Now it is a direction that this direction of this edge is v2 to v1, right? So we have a reverse direction, so we have to write here minus b. Now what is v0, v2 in u? So this is v0, v2, that is a, right? So positive a plus a, but we have already had minus sign, so it will be minus a. Then what is plus u v0, v1? Now what is v0, v1? So this is this direction, right? C, so it will be plus c. So plus c. Now similarly we can compute delta 2 of L, which is L restricted over v0, v2 minus L v0, v2, that is v1, v2, then plus L restricted over v0, v1, right? Again L restricted over v1, v2. So this is my v1, v2. So we have a positive a, right? So plus a. Then we have v0, v2. So what is v0, v2? This one, right? So v0, v2 is minus b. Now here minus of minus b, so we have plus b. Now L restricted over v0, v1. Now v0, v1 is this one, c, right? So plus of plus c, so we have plus c. Okay, so these are the images of u and L. Therefore we can write, first of all, image of del 2 equal to span of c minus a minus b and c plus a plus b. Now it can be written, if we add first two term, then we can write it is as 2c comma a plus b plus c. Okay. Now suppose we want to find the kernel of delta 2. Now delta 2 has only two elements u and L. So what is my kernel of delta 2? So let del 2 p of u plus q of L equal to 0. Now that will imply q minus pa plus q minus pb plus q plus p c equal to 0. Now since there is no relation between a, b and c, that will imply q minus p equal to 0 and q plus p equal to 0, and that will imply p equal to q equal to 0. So that's mean kernel of delta 2 equal to 0. Now again, since delta 3 Rp3, sorry Rp2 is 0, that will imply image of del 3, that is also 0, right? So H2 delta Rp2, that will be kernel of delta 2 quotient with image of del 3, that is 0 quotient with 0, that is equal to 0 map, sorry 0 group, right? So therefore second homology group of Rp2 equal to 0. But we already know that image of del 2 equal to span of a plus b plus c comma 2c. Now we want to find kernel of del 1. Now delta 1 of Rp2, that is spanned by a, b and c. Therefore let del 1 xa plus yb plus zc equal to 0. Okay, now first we need to find what is the image boundary of a, boundary of b and boundary of c. Okay, let's compute that first. So del 1 of a. Now by the image you can look at what is a. A is just v2 minus v0 and v0 is same as v1. So we can write it is v2 minus v1. Now what is the image of b? This one. So it is v1 minus v2, right? So this is v1 minus v2. Now what is the image of, boundary of c? Now if you look at what is c, that is it is starting from v0 to v1, right? So boundary of c will be v1 minus v0. But we know that v1 and v0 both are same, so it is 0. Okay, so therefore here we can write it is x v2 minus v1 plus y v1 minus v2 plus 0 equal to 0. Now that implies it is x minus y v2 minus v1 equal to 0. Now since this is one basis element, so that implies x minus y should be 0, that is x equal to y. So kernel of del 1 will be xa plus xv, since x equal to y, plus zc, where x and z belongs to the integers. So we can write kernel of del 1, that is x into a plus b plus z into c, where x and z belongs to the integer. So that is span y a plus b comma c. Now it is given that image of del 2 equal to span of a plus b plus c comma 2c, right? So we can write the kernel of delta 1 as span of, just take the sum of first two terms, so a plus b plus c comma c. So therefore first homology group of Rp2 will be kernel of del 1 quotient with image of del 2, that is span of a plus b plus c comma c quotient with span of a plus b plus c comma 2c, and which is isomorphic to span of c quotient with span of 2c, that is isomorphic to z2. Okay. Now we can compute the zeroth homology of Rp2. Now what is that H0 delta Rp2? That is, we know delta 0 Rp2 quotient with image of del 1. Now we know that delta 0 of Rp2 is spanned by, and this is also you can write kernel of del 0, right? It is spanned by V1 V2. And what is image of del 1? We have seen that here from this, right? So image of del 1 equal to span by V1 minus V2. So there it is span of V1 minus V2. Now that is, again you can write span of first subtraction of first two term, comma V2 quotient with span of V1 minus V2, and that is isomorphic to span of V2, that is Z. And since delta n Rp2 equal to 0 for all n bigger equal to 3, that implies Hn delta Rp2 equal to 0 for all n bigger equal to 3. So thus we get H0 delta Rp2 that is equal to Z H1 delta Rp2 equal to Z2 and Hn delta Rp2 equal to 0 for all n bigger equal to 2, right? Because we have already proved that H2 of Rp2 equal to 0. So this is the simplicial homology groups of Rp2. So now I shall compute the simplicial homology groups of a 3-dimensional objects. Okay. Now we shall see one problem. Say find the homology groups of Rp3. Okay, that's mean 3-dimensional real projective space. So what is Rp3 first of all? Its name is real, or you can say 3-dimensional real projective space. Okay. So how to define this Rp3? So first of all, we denote D3 by all the vector in R3 such that norm of x less than equal to 1. Okay, so this is a closed ball and S2 is a boundary of this 3 ball. That's mean all the point in X R3 such that norm of x equal to 1. Okay. So that's mean S2 is a boundary in D3. Okay. Now Rp3 is defined by D3 with some identification where x will be identified with minus x when x belongs to, that is the in the boundary of D3. Okay. So in other words, suppose you have a 3 ball. So suppose you have this 3-dimensional ball. This is a solid ball. Okay. Suppose you have a D3. Then if you look at the surface of this D3, that is the boundary of this D3, then this is my point 0. Okay. Then if suppose this is my x, then the reverse one will be in the back side will be minus x. Okay, so this x and minus x will be identified when x belongs to this S2 subset of D3. Okay, now first of all we need to find one delta complex structure on this Rp3. Okay, and then we need to find the homology groups. Fine. So how to find a delta complex structure on D3? So what we will do, we will take two simplices. Say one simplex we can write in this way. Okay, so this is a simplex. Okay, now take another simplex. So in similar fashion we can take another simplex. Okay, now if we identify this face, so this is a triangle, right, and this is another triangle. Now if we identify this triangle with this and this triangle with this, then we will have another D ball, right? So this is a D ball, this is a D ball, and we are identifying two faces of that one. Okay, so we will get another D ball, and this D ball will be look like this. Where we have four vertices. So this is one vertex, this is one vertex, this is one vertex, this is one vertex. Okay, and what are the edges? So we can write edges. So this is one edge. Okay, so this is one edge, this is one edge, this is one edge, this is one edge, and this one will be one edge, and this one will be one edge. Fine. Now if we identify, say, this triangle, okay, with the reverse triangle, this one, we can write in this way. Okay, the reverse one, and if we identify this triangle, okay, with the reverse one, say this one, then we will get Rp3. That's mean we are identifying the antipodal vertices of the boundaries. So we get this one, right? So this is one vertex, this is one vertex. So there will be these two vertices, right? There will be one edge between this. Okay. So suppose this upper tetrahedra is this one. Okay, so suppose this is my, say, V0, say this is my V1, say this is my V2, so this is V3. So that's mean this is my V0, this is V1, this is V2, and this is V3. Okay, and suppose there is another tetrahedra, the lower one. So again, say V2, V3, say V1, V0. Okay, Now so we have edges, so we can take this one red edges. So this is one edge, this is one edge, right? So this is one edge, this is a one edge, this is one, and this one edge, and this one is another edge, right? So we can call this edge as A. Suppose this is my edge A. Okay. Now since we are identifying the antipodal point, right? So this point will be identified with this point, right? Because these are the antipodal points, right? So that's mean this edge, the upper edge, will be identified with the lower edge with this orientation. So if we consider this is my A, then the lower one in this direction, that will be my A. Okay. Now suppose this is my B. Suppose this is my B. Now if this is B, then we know, so this point, say this point is identified with this point, right? This is the antipodal point, and this point will be identified with this point, right? They are the antipodal points. So we have a direction in this way. Fine. So if this is my B, then this will be my B. Now similarly, if this is my C, okay, then so this point is identified with this point, right? And this point will be identified with this point, right? So that's mean if this is my C, then in this direction that will be my C. So we have another edge, right? So this one, so we can choose this direction and we call it D. Okay. Note that for this direction of edges or triangles, you can choose any direction. So you can choose arbitrarily, but then you have to stick on that direction. Fine. So later you cannot change the direction. So here I choose this direction, you can choose other way as well. Okay. That's mean you can choose your A in this direction. In that case, this A will be in this direction. Fine. Anyway, so this is my direction for the edges, and obviously now you can check that V0 and V1 are the antipodal points, right? So they will be identified because they are antipodal points on the boundary, or you can say on the S2. So we have V0 equal to V1, and again V2 and V3 are identified. So V2 will be same as V3. Okay. Fine. Now we will have some triangles, right? So first of all, we can take a different pen, say green. So we will have 4 triangles. So this one, okay. Now this triangle one, and the back side of that one, and this one. Okay. And the reverse on the lower side, that will be identified. So for a time being, we can say this is my A, this triangle. Okay. So this V0, V2 and V3. So this triangle. So this triangle suppose is A, and call the back one is V. So this is this. Okay. So backward is V. Now since that B will be identified with this triangle, okay, so that will be my again B, and here the back side will be A. Okay. Okay, so that will be my A. We have two more triangles. Say this is my C and this is my D. Okay, so we have two vertices, four edges, small ABCD, four triangles, capital A, capital B, capital C, capital D, and we have two tetrahedra, say U and L. Say this is my U and this is my L. Fine. So therefore delta 0 is span of the vertices. So we have two vertices, say V1 and V2, and delta 1 will be span of four edges, right? So A, B, C, D. Delta 2 will be span of the triangles, say capital A, capital B, capital C, capital D, and delta 3 is span of U and L. Fine. And delta n will be 0 for n bigger equal to 4. Note that since all the maps from simplicious to X are uniquely identified by the image of the simplicious, so we can write that delta n as a span of the image of the simplicious. Okay, so without loss we can write this one. So this is just a notation. That's mean instead of the map, say sigma I alpha, we will just use that ABCD or UL. Okay. Now what is my triangle A? There are two copies of A, right? One is in U and another is in L. But we have to stick with one orientation. So here, say this is my U, this is my L. Okay. Now in U we can write A as say V0, V3 and V2, and in L we can write this is my A. Now note that in U we have V0, V3 and V2, right? So this is my A. Now note that V1 is identified with V1. So this should be same as V1, and V3 is identified with V2 in L, right? So this is V2, and V2 in U is identified with V3 in L, right? So we have to stick with one orientation for A. Now we choose this orientation. Okay. Now since we choose this orientation, here we have to stick with the same orientation, since this is just a copy of A. Okay, so this is the orientation in U and L. Now similarly we have two copies of V, one is in U, another one is in L, right? So this is my B. Okay. Now in U we have the vertices, say V1, V2, V3 in U, and in L V1 has a copy, that is V1 is identified with V0 in L, right? V2 is identified with V3 in L, and V3 of U is identified with V2 in L. Okay. Now here also we choose this direction. Okay, and that's mean we have to stick with this direction in L. And for the C and D we have same copies actually in A and B, right? So we can stick with one orientation. Okay, this is my C. Okay, so we can choose that V0, V1 and V2. So this is my orientation, and that will be same here as well. So V0, V1, V2, and similarly for the D. Okay, so for D we have V0, V1, V3. So V0, V1, V3. So V0, V1, V3. So this is the direction. Okay, so we need this fact to find the boundaries of U and L. Now first of all, what is the boundary of U? Say del of U. So we know that, so consider this U as a map. That's mean by the definition of the boundary. So this is my del 3, right? That will be U restricted over, first of all, V0 will be missed. So V1, V2, V3. Okay, then minus again U. Now V1 will be missed. So V0, V2, V3. Okay, then plus U. Now V2 will be missed. So V0, V1, V3, and minus U restricted on. Now V3 will be mixed, right? So here it will be V0, V1, V2. Okay, right. Now what is my U restricted over V1, V2, V3? Now look at the picture here. Okay, so what is my V1, V2, V3 in U? So this is my V1, this is my V2, this is my V3, right? So we have the triangle B. Fine, that is the back side of U. Now look at the orientation here in U. So this is my V1, V2, V3. That's mean we will have B. Okay. So we can just, so that's mean we can write here, this is my B. Now the next one is minus and then V0, V2, V3 in U. So V0, V2, V3. Now look at, this is my V0, this is my V2, this is my V3. So we will have A, right? So this is this front side of U. So we will have map A. Now look at this orientation here. Now what is my 0, 2, 3? See, 0, 2, 3 means in this side. But we know that A means 0, 3, 2. But here we need 0, 2, 3. Right, V0, V2, V3. Therefore, we will have minus A here. So, we will have minus of minus A. That's mean we will have plus A. Now, we have U restricted over V0, V1, V3. So, V0, V1, V3. So, that's mean we have D, right? Now look at the orientation at D, this one. So V0, V1, V3. So we have plus D here. So we have plus and plus D. And then what is my V0, V1, V2? Now again look at here. So V0, V1, V2. So that is C. Now if you look at C, then V0, V1, V2. So this is a positive sign, right? So minus of plus C. So we have minus of plus C. So this is a minus. So we have delta 3 of U equal to A plus B plus D minus C. Now similarly we can construct delta of, that is the boundary of L. Say delta 3 L. Now this will be my L. So again V1, V2, V3 minus L. 1 will be missed, right? So V0, V2, V3. then plus L, it will be, now 2 will be missed, so V0, V1, V3, then again minus L, so V0, V1, V2. Okay. Now again look at the L, that is the lower tetrahedron, and we will look at the vertices V1, V2, V3. So V1, V2, V3. Okay, so that's mean the back side of L. So that is my A. Okay. Now look at A in L. So this one. Okay. So what we have? So V1, V2, V3. So this is my positive orientation, right? So we will have plus A. So we have plus A. Okay, now next one is L restricted over V0, V2, V3. Go here. So V0, V2, V3. That's when we have the front side of L. So that is the map B. That is the triangle B, right? Now look at B, this one. Okay. So we need V0, V2, V3. So V0, V2, V3 in this direction, right? But from the given condition we have B means V0, V3, V2. So therefore we have here minus B. Okay. So we have minus of minus B, so plus B. Now plus we have L, this is over V0, V1, V3. So V0, V1, V3. So we have D. Now D means we have already seen that this is a positive sign, right? So we have similarly positive D, and since we have already seen that V0, V1, V2 means you can check this is my C. So V0, V1, V2. Okay. And we know that this is also positive orientation here. This one, right? So we have minus C. So this is my boundary of U and boundary of L. Now if we want to find the kernel of delta 3. So first of all we know that this delta 3 is generated by U and L, right? Now let delta 3 of PU plus QL equal to 0 for some P comma Q belongs to Z. Now that imply P delta 3U plus Q delta 3L will be 0. Now we know that delta 3 of U and delta 3 of L both are same, right? So we will have P plus Q into A plus B plus D minus C equal to 0. That will have, we have P plus Q equal to 0. That's mean P equal to minus Q. Therefore kernel of del 3 will be span of U minus L. So that is isomorphic to Z. Okay, so before computing the homology group, let's write the chain complex first. So we have that delta 4, say X instead of Rp2, right? So this is my, we know this is 0. So delta 3X, delta 2X, delta 1X, delta 0X, 2 0, that is delta 0, delta 1, delta 2, delta 3. Now this is delta 4 and this is just a 0 map and this is also a 0 map, we know that. Now H of 3 So this third homology group of Rp3 is kernel of del 3 quotient with image of del 4. But we know that del 4 is 0, so this is totally 0. So that is same as only kernel of del 3, and we have already seen that this is isomorphic to Z. So that is isomorphic to Z. Okay. Now we need to find the second homology group. So before that we can see that here delta 3 of U equal to this and delta 3L equal to this. Therefore, image of del 3, it is just span of this one, that is A plus B plus D minus C, only this. Okay. Now we shall find the kernel of delta 2. So let's write what is my triangle ABCD from the picture. So suppose this is my A, so this is my B, so this is my D, so C, so this is my D. Okay. So we have seen that A means we can write here this one, so V1, V2, V3. So this is V1, V2, V3. B means again V1, V2, V3. Okay. C means V0, V1, V2. You can check that. So V0, V1, V2, and D mean V0, V1, V3, and we have chosen the orientation in this way. Okay. Now from the picture we will write what are the edges of this A, B, C, D. Now look at the picture. So this one. Okay. Now if we look this picture, that is the main picture, so this one very carefully, then you can see that what is my A. A means V1, V2, V3, right, the lower part of that one. Okay. Now you can check that V1, V2 means, so B is from V2, V1. B, the small b, that is one, small b from V2, V1. Okay. So V2, V1, that will be small b. Now look at V2, V3. Here, see, V2, V3 means we have A. Okay. But we have taken that lower side. So V2, V3 means this one, that lower part triangle, right? Because we have assumed this one. So from V2 to V3 we have a reverse A. Okay. See, remember that, don't be confused with this one. So this is also V2 to V3, but we have considered the orientation from L, this one, right? So that's mean, so V2 to V3 we have reverse A. So this is a V2 to V3, so we have a reverse A. So here we have reverse A. Now similarly you can check that we will have this type of C. For B we will have this C, this A, this B. For C we will have this C, this B, and this D, and for D we will have this B. Okay, we can check that one for D. So for D we will have V0 to V3. Okay, so this is my D. So V0 to V3 we have B the reverse way. Okay. So V0 to V3 B in a reverse way. Okay. Now from V0 to V1 we have D, and V1 to V3 we have C. You can check this one again, D. Okay, you can check that V1 to V3 we have C. Okay, so you can verify all of this, capital A, capital B, capital C and capital D. Okay, now what will be my delta 2 of A? Now this is simple. Now delta 2 of A will be just in this way, so it will be minus A minus B minus C. Now delta 2B will be, now you can start with A. See, it will be going through A, right, in that direction, so A will be positive. Now what will be my B? Since it is a plus and minus sign only, so this is not necessary, you have to go through it C, A, B in this way. Okay, now look at B is going to the right to left. Okay, but in our direction it should be going to left to right. Okay, so it will be minus B and it will be minus C. Did you get why it is, how does these signs are coming? Okay, I can do it explicitly. Suppose we want to find delta 2 of C. Okay, now what is my delta 2 of C? Now if you look at B, B means B is going to V2 to V1. Okay, but in our orientation C, it is anti-clockwise, so it is going through V1 to V2. Okay, so we have minus B. So we have minus B, similarly minus C plus D, and delta 2 of D will be again B plus C plus D. Okay, now we need to find the kernel of delta 2, and we know that it is span of this ABCD. So let delta 2 of, say, x of A plus y of V plus z of C plus w of D equal to 0. Now that will imply actually, so minus x plus y into A plus minus x minus y minus z plus w B plus again minus x minus y minus z plus w C plus z plus w D equal to 0. Now since there is no relation between A, B, C, D, that means we must have minus x plus y equal to 0, that is x equal to y. We also have z plus w equal to 0, that means z equal to minus w. We also have minus x minus y minus z plus w equal to 0, but we already have x equal to y, so we have minus 2x. Okay, and z equal to minus w, so we can write 2 of w equal to 0, that imply x equal to w. So we have x equal to y equal to minus z equal to minus z equal to w. So that imply kernel of delta 2 is span of, say, A plus B minus C plus D. Okay, Now look at kernel of delta 2 is same as image of delta 3. Now we can write, since kernel of del 2 equal to image of del 3 and both are span of A plus B minus C plus D. So we have the second homology of Rp3, which is kernel of del 2 quotient with image of del 3, that is 0. That is just isomorphic to 0. Now if you look closely, then what is my image of delta 2? So image of delta 2 is this one, right? So we will have span of minus A minus B minus C, A minus B minus C, D minus B minus C, B plus C plus D. Now we find kernel of del 1. So first of all, delta 1 of Rp3 is span of the edges, that is the image of edges A, B, C, D. Okay. Now what is the boundary of A? So del 1 of A. Now look at the picture again. So where this is A, right? That's mean A is a, say here, it is a image of a edge or image of an one simplex from V2 to V3, or you can say V3 to V2. That's mean the boundary of A will be V2 minus V3. But we know that V2 and V3 are same. Therefore, boundary of A will be 0. You can say it is V2 minus V3, but they are same, so it is 0. Now what will be del 1 of B? Again this. Now here look at, this is B. Now B is a edge from V3 to V0, right? Therefore, the boundary of B will be V0 minus V3. Okay. But we know that V0 equal to V1 and V3 equal to V2. Therefore, we can write V1 minus V2. That is V1 minus V2. Now what will be del 1 of C? Now look at this one. So C is an edge from V1 to V3, right? Therefore boundary of C will be V3 minus V1, but V3 equal to V2, so we can write it is V2 minus V1. So it is V2 minus V1, and boundary of D will be, you can check, it is a edge from V0 to V1, so boundary of D will be V1 minus V0, but we know that V0 equal to V1, therefore it is equal to 0. So this is equal to 0. Okay. Now what will be the kernel of delta 1? So first of all, let del 1 of XA plus YB plus ZC plus say WD equal to 0. Now that imply, since del 1 of A and del 1 of D will be 0, therefore we will have Y del 1 of B plus Z del 1 of C equal to 0, right? Now that will imply, you can write Y minus Z V1 minus V2 equal to 0. Now since there is no relation between V1 and V2, that imply y equal to z. Therefore, kernel of del 1 is span of, or you can write it is equal to, first of all, xa plus, since y equal to z, so you can write y b plus c plus w d, where x y w belongs to z. So this set, right, that's mean it is a span of a, b plus c and d. Now if you assume that b plus c equal to e, now then kernel of del 1 will be span of a, d, e, right, since b plus c equal to e, and image of del 2 in terms of a, b, e, it will be span of minus a minus e, a minus e, it will be d minus e and d plus e. Okay. Now if you take the summation of first two and the summation of last two in two places, then it will be equal to span of, so first take this two, summation of these two, so it will be minus 2e comma a minus e then if you take summation of this and this, okay, we will not take the summation, what we will do, we will take subtract this from this, okay, then we will have minus 2e and d plus e. Okay, so we can do this one because this is just a span, right? Now since we have 2 of 2e, then we can remove 1, that's mean it is a span of, you can write a minus e, d plus e, and also you can just write 2e. Okay, so this is my image of del 2. Now what was my kernel of del 1? Kernel of del 1 was span of a, d and e, right? Now again one can write it is a span of, since we can add and subtract the basis elements, so we can write a minus e, d plus e and e. Okay, so therefore H1 delta, that is the first singular homology of Rp3, is kernel of del 1 quotient with image of del 2, which is equal to span of a minus e, d plus e comma e quotient with span of a minus e, d plus e, 2e. And since this term and this term and this are same, so it is isomorphic to span of e coefficient with span of 2e, so that is isomorphic to Z2. Okay, now we will compute the zeroth homology of Rp3. Now what is my H0 delta Rp3? Now we know that is delta 0 of Rp3 quotient with image of del 1. Now what is my delta 0 Rp3? So this is span by V1, V2, right? And what is my image of del 1? We have seen that image of del 1, you can see here. So del 1 of, so boundary of A is 0, boundary of D is 0, and boundary B is V1 minus V2, and boundary of C is V2 minus V1. Therefore, image you can write it is a span of, say, V1 minus V2. Now again you can write it is a span of V1 minus V2 comma V2 quotient with span of V1 minus V2. Now this is isomorphic to span of V2, and that is Z. Okay. Now again your del n Rp3 equal to 0 for all n bigger equal to 4. Now that imply Hn delta Rp3, which is kernel of del n quotient with image of del n. Now if n greater equal to 4, then all of them are 0, so this is just 0. Thus you can say H0, that is zeroth homology of Rp3, is Z, first homology of Rp3, that is Z2, second homology of Rp3, that is 0, H3 Rp3, that is again Z, and for other that is 0 for all n bigger equal to 4. Okay. So this was the one example which I wanted to do. So we stop here. So in the next lecture I shall start singular homology. Okay.